We are now going to go through a little bit of the math that's associated with the derivation of electromagnetic waves. Now, the book does actually a few pages of this, but the feedback I've received from students in the past is that you really need to have had multivariable calculus to follow this derivation. Now, I know that many of you have not had multivariable calculus, so we're not going to work through the derivation in detail. I'll show you the answer and we'll try to interpret it. If you have had multivariable calculus, I do encourage you to read through and try to follow along the derivation that the book does, making sure that you understand every step of it. This is one of the most important derivations that can be done in introductory physics, as it fundamentally shows that light is an electromagnetic wave. So the conclusion that we get to after using the source-free Maxwell's equations is this wave equation here. Now, if you think back to when we studied the basics of waves, there was the idea that all waves, if we define a displacement capital D, are defined by an equation like this, where you have a coefficient of proportionality that is actually your speed squared. So we get to this form, and again, it has this general form where your displacement in this case is the electric field. Now we could do this for the magnetic field, but you just need these two displacements to be the same. So we have the electric field. Note that it's in the y direction. Here we're assuming that it's propagating in x. And there's nothing particularly special about the y direction. We'll just define the y direction to align with the electric field in this situation. That we have our second time derivative, again this is a partial derivative, is equal to this value, which is coming from all of those Maxwell's equations. So really this term here is coming out of the derivation itself, the math that you do to get here. Then we have our position derivative over here. So what's exciting about this is we see that this is equal to speed squared. Now this is the speed of propagation of our electromagnetic wave. Now for other types of waves, such as a wave on a string, this would have to do with the properties of the medium that the wave travels in. But at no point in the derivation do we need to do that. We're just using Maxwell's equations as they are. And so this means that our speed of an electromagnetic wave is 1 over the square root of these two constants. Remember that one of these constants, epsilon naught, was coming from electric fields, and mu naught was coming from magnetic fields. And we get this value if you just plug in what those constants are, and this is c. This is the speed of light. So fundamentally, we derive from theory what the speed of light is from these two constants. And again, it comes from using the source-free Maxwell's equations to get here. Now, scientists can go and measure the speed of light, and you actually get the same value. So this is really exciting. We see that there are these self-sustaining electromagnetic waves that have electric fields and magnetic fields in them. From theory alone, we can calculate what the speed is, and we see that the speed matches what we measure for light. So this in itself is really the proof that light is an electromagnetic wave. Now, we've studied interference and diffraction, which also gives us clues that light is some sort of wave, but this is a really big deal here, that from theory alone, we can see what speed light travels at. Now, the next thing to recognize is that we need to have the direction of propagation and how that relates to the individual fields. Now this is something kind of a little bit separate, but I chose to put it on the same slide, and we can use the right-hand rule. So we have E cross B. So use your favorite version of the right-hand rule to do E cross B, and that will give you V, the direction of propagation. So notice that when you do E, for instance, here it's up, B is kind of this positive Z direction, that you then get V being this way. Now what's interesting is that a little bit later, E is now down, B is that way, but when you do E cross B, you again get your direction of propagation that way. So even though E and B are going between, for instance, positive and negative Y, positive and negative Z, you still always get the same direction of propagation. So please make sure that you can understand how to do that. If you need to go backwards, for instance, if you have B and you have the direction of propagation, you're trying to find electric field, you can always guess and check. You know that they have to be perpendicular, so once you have two of them, that really just leaves two possible directions, and you can use the right-hand rule to check. So this is pretty interesting. We've used our wave equation, we've gotten to the form that we know that there's then going to be traveling waves, and of course standing waves come from traveling waves. We get the speed, and we've been able to define something about our direction of propagation. Now, if we want to talk about a functional form, we can talk about sinusoidal waves. So sinusoidal waves are what satisfies that wave equation that we just described. And as we talked before, in waves, we can talk about it with k, wave number, and omega, angular frequency, or we can talk about k as 2 pi over lambda, the wavelength, and 2 pi f is your angular frequency. So these are just different variables that we can use. So now notice that it is a function of x because that is the direction of propagation, but in this case, electric field is in y and magnetic field is in z. And if I go back up, you see that magnetic field always lies on the z-axis, electric field is always pointing in the positive or negative y direction, but it's propagating in x. So it's a function of x, we get a z component for magnetic field, we get a y component for electric field. Now, something to notice here is that the arguments inside here are the same. So this means that the phase difference between these is 0. Wherever you have a maximum for your electric field, which would be some argument here that gives you sine equals 1, you also would have the same thing in B. And again, this matches what we see here, that the peak of E occurs at a certain spot in X, and you have the same thing for B. Where you have a 0 value for E, you have a 0 value for B. So we say that these are in phase. And again, mathematically, the same thing happens here. So now we can actually relate electric and magnetic fields. So this is a condition coming from Faraday's law. Again, part of the derivation that we're not going to go through in detail. Understanding where this equation comes from requires some understanding of multivariable calculus. But notice that we have a spatial derivative of E with respect to x, and we have a time derivative of B with respect to t with a minus sign. So when we actually go back up and say, okay, I'm going to take my spatial derivative of this, so sine of x, we have some constants that come out and sine becomes cosine. And then we take the time derivative here, notice that there's a minus sign here. So there's a minus sign there, the derivative gives us another minus sign, so we're left with these two forms. We have cosine of some stuff in both of them. Those are going to be the same. So all that this is enforcing is actually the coefficients. Both of them have a 2 pi, so what this leaves is E naught, and E naught, if we look back up here, was the maximum value of your electric field. So this is the amplitude. That we're left without over lambda equals F, your frequency, times B naught, which is then the maximum value of your magnetic field or your amplitude in B, and we can multiply lambda up. So that's how we get to this first value here. So we see that we have a constraint on the relationship between the value of electric field and the value of magnetic field. However, lambda f is just the speed of your wave, which here is c. So what we typically do is write it this way. Now there's a really important interpretation here. One is that this is telling us about the amplitude of our waves. The maximum value in E is equal to C times the maximum value of B. Now remember that the electric and the magnetic fields do not have the same units. So this is kind of interesting because C in fact does convert the units appropriately, but it's going to give you a numeric factor as well. However, notice that here with the derivative we have that cosine form, and previously we had that sine form. It's not just the maximum value, because your argument of the wavy part, right, the cosine or the sine, because the argument of that is the same, whatever electric field value you have as a function of space and time, that is going to be equal to C times the magnetic field for the same position and the same time. Now notice that I'm not writing this as a vector because they do point in the different directions. This is E is in the y direction, B is in the z direction. But the magnitudes are the same, and this has to be true at every single spot on the wave, not just the maximum value, every single spot. So what this means is that when we're dealing with electromagnetic waves, we are typically going to work either with the electric fields or with the magnetic fields, that these aren't really independent fields. These aren't independent values. There's this enforced relationship between them. So to just show you a little more explicitly, again, if we go back to the sinusoidal form and we plug in C B naught for E naught, that shows up here. And so then again, we see that these components are the same. The only way that our original relationship then works is if this is always true. So again, feel free to always work with whatever component you're comfortable with. Sometimes you're going to be asked if you have a specific value of electric field in a wave, what's the value of the magnetic field? And all you have to do is use this conversion.